Okay, it's working, right? Okay, let me grab my thing. Okay, welcome everyone. Thank you for joining. Today we talk about AWS Lambda, how it's built, how it works, and why it's so cool. My name is Danilov. I'm a senior principal engineer at AWS Serverless. A decade ago, I joined EC2 networking team, and it was a fantastic ride. And then, 5 years back, I heard about Lambda. And I really liked the simplicity of the idea. We run your code in the cloud, no servers needed. So I joined them. Today, I'm excited to share some of the great stuff I've learned along the way. Let's get started. So this is our agenda. So first, I will do introduction to the Lambda itself, so I understand key concepts about the service and its fundamentals. It will help us understand and deep dive. Then we'll talk about Invoke routing layer. It's a super important part of the system which connects all the microservices and makes system work together. Then we'll talk about compute infrastructure. This is where your code runs. This is servers and serverless. And then, alongside our conversation, I will tell you a story about cold start. So what is Lambda? Lambda is a serverless compute system. It allows you to execute your code on demand. You don't need to own, provision, or manage your servers. Lambda has a set of built-in languages, so you provide only your code, and we execute it. Lambda scales fast with response to your traffic demand. Lambda launched 9 years ago, and today, millions of users use it daily, monthly. They together generate trillion invokes every month. It's a big volume. So let's see how it works. These are examples of very simple hello world functions. You only write your code. You can pass your data in an event, and then context will provide you some runtime information like request ID, remaining execution time, etc. Configuring Lambda is very simple. You only pick preferred memory size. All the rest resources, including compute, CPU, will be allocated proportionally. Lambda supports 2 invocation models. First is synchronous invoke. In that case, you send a request, it gets routed to your execution environment, your code gets executed, and you receive response synchronously on the same timeline. In asynchronous invoke, your request will be queued first, and then it will be executed at different timeline by polar systems. It's important to highlight that execution of asynchronous invoke is no different from synchronous. It's important because today we'll only talk about synchronous invokes. Before we start, it's also very important to talk about Lambda tenets, because they help us to make technical trade-offs, make technical choices, and design decisions. So first is availability. We want to ensure that our service is available, and every time you send us a request, you receive reliable response. Efficiency is super important on-demand systems, because they need to be able to provide resources very quickly and release them very quickly as well to avoid wastage. Scale, as I said, Lambda scales very fast with response to your demand. And it also scales down very fast as well, again, to reduce wastage. Security is job number 1 in AWS, and Lambda is no exception. We want to provide you a safe and secure execution environment where you can run and trust your code. And performance. We're building a compute system. That means we want to provide very little overhead on top of your application business logic. We want our system to be invisible. This is very high-level overview of Lambda component. And don't worry, today we don't have enough time to go over every block. We'll only talk about invoke routing, and compute infrastructure. So let's start with Invoke request routing. So this is the layer which connects all the microservices together. It provides availability, scale, and execution, access to the execution environments. But let's start very simple. Let's build it ourselves. So we have an Alice, and she asks us for help to run her code in the cloud. So first, we need to add a configuration service of some kind to store her code and associated config. Then, we need to introduce a front end. Front end will take an Invoke request, validate it, authorize, and then look up stored configuration in a database. And now, we need a worker with execution environment, or sandbox, how we call them, where actual Alice's code will run. Sounds simple, but there is a problem. Remember, we are building on-demand compute system. It means at the time of the invoke, there may not be an available worker or execution environment. So front-end doesn't know where to run code, where to send a request. Let's add a new system. We call it placement. Placement will be responsible to creating execution environment or sandboxes on demand. So now, front-end needs to first call placement to request a sandbox. And only after that, it can send the invoke request to the created execution environment. So now it's functionally complete. But there is a problem. So we added on-demand initialization in front of every invoke request. And this initialization takes these many steps. You need to create execution environment itself. You need to download customer code. You need to start up a runtime. And you need to initialize the function itself. It all can take several seconds, which wouldn't be a great customer experience. This is latency distribution graph. It shows how often we see a particular invoke duration over the period of time. The green invoke latency is our good work. This is what our code does. It's our business logic. It does some useful work, and it takes some CPU time. It's OK. And we want our overhead to be very minimal. So that's why we want to be nearby in terms of observed latency. But what we see, we're here. This is because of all these initialization steps we're taking in front of every invoke. It's not great customer experience. So let's fix it. Let's introduce a new system. We call it Worker Manager. Worker Manager will be responsible to help us reuse previously created sandboxes and use them instead of creating new one every time. So now, we have two modes. The first fast one, when front-end asks Worker Manager for a sandbox, and Worker Manager returns one. And then front-end sends an invoke without significant interruptions. We call it warm invokes. Still, there are some cases where Worker Manager won't have a sandbox. So it has to call placement again to create new one. This would be our initialization path, slow path. This is how it's seen on the distribution graph. We now see kind of two bumps. One, we see that majority of invokes now move to the right spot. They provide very little overhead. They are fast. We call them warm invokes. And there is a smaller number of the cold invokes still left. A little spoiler, by the end of this talk, we'll completely eliminate cold starts. But there is a lot of needs to be done. So let's continue. This is more realistic representation of Lambda in synchronous invoke routing in production. We added multiple availability zones for resiliency. We added front load balancer to distribute the load. And we replaced Worker Manager with assignment service, and I explain you why in a bit. But everything else looks very similar to what we just built for Alice. So let's deep dive into the Worker Manager. Worker manager was the original system which was built when Lambda started. In order to track sandboxes, it keeps in memory database of all the created sandboxes and their state. Sandbox can be in busy state, meaning it's serving an Invoke, or it can be in idle state, meaning it's doing nothing. So when a reserve request from front end comes in, worker manager will pick first available idle sandbox and return. It also will mark it as busy, and worker manager will track the progress of Invoke to mark it as idle at the end of the Invoke. This is how worker manager was deployed into the production region. Again, we have multiple zones. Worker manager deploys in every zone. And because Lambda is a regional service, worker manager was tracking sandboxes in every other AZ availability zone. And the system works reasonably well. It was available, it provided scale, until it doesn't. So remember, every worker manager holds sandbox state in memory, which is not durable storage, it's not replicated. So if for whatever reason a worker manager host goes down, we lose all the sandboxes which was created by that instance. Let's look at the production region. In the case of availability zone event, we generally expect that, okay, we will lose 1/3 of capacity which resides in this availability zone. And the rest availability zones will scale to compensate. Because worker manager tracks sandboxes in multiple availability zones, the real impact would be worse. We will lose capacity in healthy AZs as well, because they was tracked by unavailable worker managers. The compound impact can be quite large, and it's not acceptable. In addition to that, worker managers, they run in isolation. So all the remaining worker managers, they will start calling placement service to compensate for the losing capacity, adding additional load and pressure on the system in the case of availability event, making it harder to recover. This is why, a year ago, we replaced worker manager with a new service called assignment service. Functionally, it looks exactly the same. It runs in every availability zone and tracks sandboxes. But there is a difference. We added reliable, distributed, and durable storage. We call it journal log. This storage tracks sandbox states across the entire region, and it's replicated across multiple availability zones and multiple nodes. So now, we were able to organize assignment service in partitions, usually about 3 nodes each. They have 1 leader and 2 followers. And they coordinate their work based on the distributed state. Only leader is allowed to write to a log. And only leader is allowed to call placement to create new sandboxes. Followers, they only read only replicas. So they just follow and read the journal log. In case of leader failure, a follower can easily take over and become a new leader. No sandboxes will be lost, and it will be able to continue where the previous leader stopped. Thanks to the distributed state, we can easily introduce a new node, and it will rebuild the state from the log. And now it continues, easy to serve. This change helped us to significantly increase availability of the system. It became fault tolerant to a single host failure, and an availability zone event. We replaced in memory state with the distributed, consistent sandbox state regionally. And we applied leader-follower architecture for the quick failovers. Additional benefit that new service was rewritten in Rust. And Rust is an awesome language. It helped us to increase efficiency and performance of every host, improving processing volume, and reducing overhead latency. So this is the end of chapter 1 about Invoke routing. So we learned about cold and warm invokes. And we learned about how consistent state helped us to improve availability. So now it's time to switch to Compute Fabric. Compute Fabric, it owns all the infrastructure required to actually run your code. This is the overview. So first of all, we have worker fleet. Worker is an EC2 instance where we create execution environments and run your code. We have a capacity manager, which is responsible to maintain an optimal worker fleet size. It can scale and scale up and scale down depending on demand. Capacity manager is also responsible for the worker health. It can proactively detect workers in unhealthy state and replace them with the healthy ones to minimize traffic disruption. You remember placement from Invoke routing. Placement is responsible to creating execution environments. But before it can actually create, it needs to pick a right worker. Worker in an optimal state to take a new work. And our data science team helps both services, placement and capacity manager, to make smarter decisions. Data science team takes a lot of production real-time signals. They build models and share them with capacity and placement. So both teams can forecast and make smarter decisions. And it works really well all together. Let's quickly look again at the routing. Remember, we helped Alice to run her code in the cloud. Now Bob asked us to do the same. So question, can we run Bob's code on the same worker as Alice? The answer is maybe. So let's deep dive into the data isolation. The most straightforward thing would be to load Bob's code in the same runtime process as Alice. But it would be a disaster, right? Because now both functions can write to the same memory, they can interfere with each other. We want to separate them. Operating system provides us a good logical separation boundary process. So we can launch multiple runtime processes, one for each function. And in case they will be logically isolated, we can even put them in containers for the additional isolation. But it's not sufficient, because we run arbitrary code in a multi-tenant system. We don't know what this code is doing. And there are plenty of security threats which can escape process boundary. This is why in AWS Lambda, we believe that only virtual machine isolation provides sufficient guarantees to run an arbitrary code in a multi-tenant compute system. When Lambda launched, we were using EC2 instances, EC2 VMs as isolation boundary. It means single tenant worker. In this world, no, you cannot put Bob's code on the same worker as Alice. We would create an execution environment on such worker and then run code. And it works fine logically and provides good latency. But there was a problem. So first is waste. Even a smaller EC2 instance is much larger than the smallest Lambda function. It means a lot of unused EC2 resources. We can fix it by creating multiple instances of the same function on the same worker. Because they belong to the same account, we're not worried about data isolation. And it's help us with the resource utilization. But there is a problem. It's very likely that multiple instances of the same function, of the same code, very likely will access system resources at exactly the same time. They will do either compute work or start doing networking or block device I/O at the same time, causing overloading of the instance. It's very hard to control this instance and provide consistent execution performance to our customers. Additionally, because we now give every account, every customer, plenty of workers, the worker fleet size became just too large to efficiently manage. Networking layout became very tricky because it's hitting standard operating system limits. Deployments, operation support, all become very tricky. And this is why we came to EC2 team and asked, okay, how they can help us. And we work, and this is how Firecracker was born. Firecracker is fast virtualization technology. It allows you to create secure and fast micro VMs. It was specifically designed to meet serverless compute needs. So this is how Lambda adopts Firecracker. So now, in every worker, we wrap every sandbox, every execution environment into tiny virtual machine. This machine is completely independent. It has its own Linux running, its own kernel, and it shares nothing with the other processes. It's secure. In this model, we can safely put multiple different accounts on the same worker. In this model, we can actually run Bob's code on the same worker as Alice, because Firecracker virtualization will provide strong data isolation. This is comparison of the size of EC2 metal instance, which we use as a substrate for the Firecracker VMs. They're really huge. They have plenty of memory. And this allows us to multiplex and place thousands of functions from different customers on the same worker and still provide consistent performance, because now they're all different. And it's very unlikely that they will request CPU at exactly the same time. More likely, it will be actually distributed and decorrelated. And placement using data models, they can pick and combine, group together most optimal workloads. Let's summarize the benefits of Firecracker. So it provides strong isolation boundaries. It's very fast and provides very little system overhead. And it enables us to decorrelate demand to resources and better control heat of our worker fleet. Let's take a look again at our latency distribution diagram. By switching from EC2 to Firecracker, we were able to significantly reduce the cost of creating new execution environment. But we still have the middle part, and we don't control it. It's size of the code, it's startup time of the runtime, and initialization time of the function. How we can fix it? Since we switched to the Firecracker VMs, we probably can use VM snapshots. This is the idea. What if, at the end of initialization stage, instead of serving Invoke, we will actually create a snapshot of virtual machine. And then, next time we need to create new VM to serve and Invoke, instead of initialization, we'll resume it from snapshot. And if resume is fast enough, the total overhead won't be noticeable different from the warm Invoke. Let's try to build it. So let's start with the rough design sketch. So first we need a worker where we launch a VM and initialize the function, run all initialization steps. At the end, we will create a snapshot. We need to upload it to some distributed storage, let's say S3. And then a different worker would download snapshot to create a local copy. And now we can create multiple VMs very rapidly. So this is definition of a snapshot. It has multiple files on disk. So first is memory file. It's the all state virtual machine accumulated during the initialization phase. Then there is a reference to the source read-only image, which contains operating system, runtime, and your code. There is also read-write overlay, which has all the data which was written to the disk during initialization phase. And then there is a smaller internal file which tracks the VM state itself. So let's summarize the ask to build such a system. So we need to find a way how to distribute snapshots between workers. We need to be able to resume multiple VMs from the same snapshot file to avoid multiple downloads. And it needs to be super fast. We will start with the resuming VMs. So Firecracker resumes VM from snapshot by memory mapping a snapshot memory file and then attaching disks via virtio interface. So the disk is kind of very standard. It's not different from the on-demand launched VM. So this is why let's deep dive into the memory map. We need to understand how it works to decide if it's safe to use in our Lambda environment, in our multi-tenant compute system. Memory mapping allows you to literally map a content of a file on a disk to a virtual private space of the running process. So when process accesses the memory, it doesn't know about file. It thinks it works with the memory. Operating system does all the magic. When process writes to such memory, operating system will copy original pages to the private memory part, and it will hold the latest overwritten pages. So this system works well and for decades, and it definitely supports multiple processes mapping the same file into their processes. Let's take a look deeper. Access to the file disk is slower than to the memory. This is why operating system adds a page cache. It's a memory place which holds content of the original file. So when multiple processes map the same file and try to read it, they actually read from this page cache. They're not going to disk. And this page cache means that multiple processes reference the exact same physical memory pages, which is what open threads in the multi-tenant execution environment. Specifically, these kind of two papers, really great examples of sophisticated side channel attacks, which leverage shared memory so that one process can influence CPU cache. And using timing, infer private data of the other process, like, for example, encryption keys. I will provide references at the end of the talk for folks who wants to read on their own. Really great read. But that means that we cannot use this proven technology in our multi-tenant execution environment. We need something better. So we introduced our own indirection layer, which enforces strict copy anytime a process accesses the data. We call it copy on read. It guarantees that there is no shared memory, hence no security threats. But we're not done yet. When we resume multiple VMs from the exact same snapshot, they're identical. Every bit of these VMs is identical. They have same random sequences. They have same identifiers, same timestamps, everything. If we allow them to talk to the internet, remote host won't be able to distinguish them. They will be confused who is talking to them. We need to fix this. This is an example of the quite real code, which uses UUID as a sandbox ID to uniquely write to a log. If we create multiple VMs with that code from the same snapshot, they will all have the same exact sandbox ID. and logging will be very confused. In order to fix that, we need to restore uniqueness of every clone VM after the resume. And it needs to be done at every layer. We need to resume randomness in Linux kernel. We need to restore uniqueness in system libraries like OpenSSL, for example. Runtime in your own code all needs to be fixed. It's a lot of work. And we start incrementally. So, together with Java community, we introduced callback interface. You can use it in your code to subscribe to the resume notification and use it to restore uniqueness of your code. We also prepared patch for the OpenSSL to reset entropy pool in the event of resume. And we're working with Linux community. We have a patch to reset Linux kernel randomness on resume. There is a lot of work to be done, but we're moving in this direction. So now we can safely resume multiple VMs from the same snapshot, and they will be unique. Let's talk about snapshot distribution. Remember, snapshots can be quite large, up to 30 gigabytes. M5 Metal disk EC2 instance has throughput of 25 gigabits. It means it will take at least 10 seconds to download entire snapshot. It will be actually longer than running on-demand initialization. So we need to do something better. When we start watching video, we're not waiting for the entire video file to be downloaded to our browser. Browser gets few initial bytes, start playing, and the rest is downloaded in background, and we do not notice it. Let's use this as an example and build similar system. So we have one large snapshot. We will split it into the multiple chunks. We choose 512 kilobytes as a chunk size. So now, we only need to download minimal set of chunks to resume a VM and start the Invoke. And the rest will be downloaded on demand. And it has two benefits. It allows us to amortize the download time during the Invoke duration. But also, we will be downloading only minimal needed working set. In most cases, this data in snapshot file is for reference only, and it's not actually used during the Invoke. A lot of data was written once during initialization time and never accessed again. So this on-demand loading helps us to only extract the working size needed for the Invoke. So this is how it will work. So remember, we have VM memory, which is mapped to the snapshot file. When process accesses the memory and its page is there, it's just immediately get the data. If page is not in memory, it will fall back to the snapshot file, and if snapshot file has the chunk, data will be returned. If snapshot file doesn't have a chunk yet, it will make a call to our indirection layer and request for a chunk. Indirection layer first will look up in the local cache on the worker to see if such chunk is available. If not, it will ask a distributed cache. And if chunk is not there as well, it will go to origin, to S3 in our case. This is how on-demand chunk loading works. Efficiency of on-demand chunk loading hugely depends on the success hit ratio of caches. Local cache is super fast, distributed cache fast as well, and origin is slow. For the consistent customer experience and stable performance, we want to ensure that we hit cache all the time, or most of the time. and minimize calls to the region. In order to maximize cache hit ratio, it would be good to share common chunks. For example, multiple Java functions, they all have Java. And it's very likely that these chunks holding Java bits will be common. And we should be able to dedupe them. Or multiple container images, they're using the same Linux. We should be able to dedupe these Linux chunks and share it between multiple functions and don't copy them. But we need to be careful because we don't want to share function data itself. It's private, it's confidential. We can leverage the fact that we know how we created these chunks because it was our system which loads operating system first, then loads runtime, and then function code. So we can create multiple layered incremental snapshots. But first with the base operating system snapshot, which has no customer data, it's just Linux booted. Then we can use this snapshot to resume VM and let's say load Java. Or different VM and load Node.js, but they still will have common operating system chunks. Then we can create next incremental snapshot. We call it runtime snapshot. And now we can create multiple Java functions from the same Java runtime snapshot. They will have unique function data, but also common operating system and Java runtime chunks. As a result, we can mark entire snapshot and tag them as operating system chunks, runtime chunks, and function chunks. And for every layer, we will use different encryption key so they don't share with each other. And for the function chunks, we will be using customer managed key to make sure that only this particular customer has access to their chunks. And they never shared. But we can share operating system and runtime chunks. This is super helpful. Sometimes we don't know the origin of the file. For example, read-only disk. We don't know what was written in the Java runtime distribution or into the Linux distribution. But still, intuitively, we think there is some common chunks there, some common bits there. So we come up with the convergent encryption idea. It means that if two chunks from two different files have the same content in the plain text, they will be equal in the encrypted form as well. In convergent encryption, the key is inferred from the content itself. So now we can take different Linux distributions, chunk them and encrypt them, and then compare encrypted chunks and be able to still deduplicate common bits. And it allows us greatly reuse chunks across container images. It altogether increases cache locality, number of hits to the local distributed cache, and reducing latency overhead. This is overview of the system in production. The only big difference is that I replaced Vogue in direction layer with a sparse file system, which actually do all this magic to request chunks and provide it on demand at a file system level. So now we're able to distribute snapshots and we're able to resume VMs. Everything should be good, right? Unfortunately, we still see some delay and some number of cold invokes. They are very close to the target place, but still we see them. Let's understand what's going on here. We need to go back to the page caches and memory mapping. Because file on disk is slow to read, operating system makes another optimization. When a process reads single page in the memory, operating system will actually read multiple pages. It's called read ahead. The expectation that in normal files, the read will be sequential. So that means we read a bunch of pages from file once, and then we just use memory because it's already there. Very fast and very efficient. Remember, we mapped memory instead of regular file. And memory is random access. So in that case, we won't hit the pages we load. We will hit every time new page. And as a result, in this example, we randomly request 4 pages, but it forces operating system to actually download the entire snapshot file. It's super inefficient. It takes time to download this file, decrypt them, checksum them. And this is what we see on this latency distribution graph. We need to fix it. It's not a QR code. So this is the memory access between 100 VMs, laid one on another. You can see that most of the pages, they're quite consistent, exactly the same spot. We can record this access pattern into a file, page access log, and attach it to every snapshot. And now when we resume snapshot, we know exactly what pages will be needed and in which order. And it becomes fast. So now we solved problem with cold starts. And the best part, you can try it today yourself. Simply enable Lambda snap start on your Java function and see how VM snapshot works. Let's summarize. So today, we talked about Invoke routing layer in Lambda. And we were able to improve availability of our system and maintain its scale. We talk about compute infrastructure. And we introduced Firecracker to greatly increase efficiency while preserving strong security posture. We also substantially increased performance of our system and completely eliminated cold starts. And all of this work is needed for a simple idea. We run your code in the cloud, no servers required. This is why we say Lambda is compression algorithm for our experience. Thank you. I collected additional materials on this link. Take time to snap it and read on your own time. Let's connect on LinkedIn. I would love to stay in touch. And I'm looking forward to talk to all of you during the next 3 days at our conference. And finally, please vote and leave feedback. You're important, super important for us. It helps us to make our sessions better. Thank you.
We have 7 minutes if you want to ask any questions.
Hi. For convergent encryption, you are using hashing to identify the chunks. What about collisions in this case? For convergent encryption, you are hashing.
So the question is how we avoid hash collisions in the convergence encryption. So we rely on the cryptographic hash algorithms to provide us reliable information. And I also think that, so I think we just rely on the cryptographic hash algorithms to solve it.
Hello, thank you for the presentation. Actually, I have 2 questions. And the first one, I think is out of scope, the presentation, but it's related to configuration. how actually you load configuration to your function, because it's at least additional whole configuration service to take it. Do you have kind of good optimization receipts to this part?
Okay, the first question is how we actually load function configuration, because making an extra hop is inefficient. It's absolutely true, it's inefficient. So in fact, front-end maintains a coherent cache of the configuration database in nearby. It's distributed cache in multiple availability zones, so it's basically become a fast cache lookup.
And now the second question. Currently, in our company, we're trying to build a Lambda function in our own data center, and we're trying to use Knative. And when we go inside and look how it works, we just realize that it's the same code, the same microservice, the same runtime, and actually, what is the benefit we can provide to our developers with Lambda function? Because they already can write it to microservices with Quarkus and Firecracker.
I think it's probably good follow-up talk after our in the hallway, because it's not directly relates to my talk here, but I'm happy to follow up in the hallway. Oh, this person. Okay.
Hi. I was curious, Nitro has brought really fast boot time to CC2, and they're really busy with 2 snapshots and a lot of similar techniques. Do you see the same kind of like snapshot technique produce kind of fast startup times to CC2?
So the question is if there is any resemblance or overlap with the EBS snapshot technology.
I guess the question is like, could you use the same techniques we showed in this talk to make CC2 instances move a little bit?
Yes, logically. So, okay, question was actually, can we use the same technology to boot EC2 instances faster? Logically, yes, but they are more complicated in terms of hardware, and virtualization layer is more complicated than Firecracker. So this is why, but yeah, logically it's possible. It's just requires more work. Yeah.
Thanks for the presentation. How do these different services, like placement service, availability service, talk to each other? Like synchronous HTTP calls or asynchronous, how do they communicate with each other?
It's basically a mixture. In some cases, it's a synchronous request-response communication. In some cases, we leverage gRPC and HTTP to streams to stream data instead of a single request response. So it's really a mixture depending on the requirements of particular communication. And so yeah, so we just find one which fit the best.
Quick question. You mentioned several times that you're using metal instances, right?
Yep.
Why is it actually metal and not regular instances?
Okay, so why we use metal instances? The Firecracker actually requires either metal instances or nested virtualization. And unfortunately today, the nested virtualization doesn't provide, doesn't meet our requirements on overhead and latency. So that's why we use only metal, because they basically fits the need. But again, logically, you can use nested virtualization, but it would be much slower. It would be 10 to 20x slower on every system call.
How do you manage the updates to snapshots and Lambda function one day or two?
Sorry.
How do you manage updates to Lambda function as well as the snapshot? So snapshot is being executed, but before
Yeah.
progress, right?
So the question is how we handle Lambda function updates while snapshot is being executed. So basically, on a creation of the function or function update, we would kick off the asynchronous background process to create a snapshot. While it's not finished, you will be using previous function version. Once snapshot is finished, we will switch to the latest. Okay.
Next question.
Last question.
Because lambdas are so granular, the amount of billable work a customer does each time one is invoked can be really small. I assume you have to make your data and control point systems very efficient to keep margins. How is that born into the engineering process? And how do you design your system?
Okay, so the question is how we handle efficiency into the engineering process. So we have three big pillars. It's security, efficiency, and latency. And as engineers, you're always kind of in a tension. You want to be in the middle of this sport because they all pull in different sides. So it's really a balancing act. There is no magic, no silver bullet here. So we always kind of try to do the balancing act, and the only thing you cannot sacrifice is security. So sometimes you can, for example, do this security patch and then restore the efficiency, but the only true kind of, you cannot do this with security, so security always first. But yes, it's a balancing act, basically, and every engineer doing this balancing act and trying to preserve all three.
Okay, that's all the time for questions we have. The next talk will be at 11:45. That'll be the relational data at the edge talk. Mike will be around for about 20 minutes for the next talk, so thank you, Mike.
Thank you.